In this video, we introduce the real line, discuss different kinds of numbers that fall on the real line, and how they can be represented using decimal expansions. We also briefly discuss approximations, significant figures, and scientific notation. All of the numbers you use or meet in this course may be regarded as falling on the real number line, indicated like this, extending infinitely to the left and to the right. Somewhere in the middle is the number 0, and you can see the counting numbers 1, 2, 3 going to the right, and the negative counting numbers going to the left. These points that I've indicated are called integers. And in between there's lots of other numbers. For example, halfway between 0 and 1 is the number 1/2, which has the decimal expansion 0.5. Okay. Halfway between 1 and 2 is the number 1.5, or 3 on 2, which has the decimal expansion 1.5. Now if we go, say, a third of the way between 0 and 1, somewhere like here, we have the number 1/3. And if you divide 3 into 1, repeatedly you just get lots and lots of 3's that go on forever. We say 1/3 is 0.3 repeated. If we look close to 1, there's a number here, say 6/7. Okay, and if you divide 7 into 6 repeatedly, what you get is 0.857142, and then the digits repeat 8557142 forever. So we say 6/7 is 0.857142 repeated. Now let's have a closer look at 1/3. 1/3 is 0.3 repeated. So what should 2/3 be? It stands to reason that that should be 0.6 repeated. So what should 3/3 be? It stands to reason that 3/3 should be 0.9 repeated. But notice 3/3 is actually 1. So what we have is that 1 has this decimal expansion 0.9999 going on forever. Okay. So if I take 1 and I look at this decimal expansion and say truncate at, say, the third decimal place, I get 0.999, which is a little bit less than 1. If I go further along and add more 9's and stop, I still get a number which is a little bit less than 1. The further I go along this decimal expansion, the closer I get to 1. And if I imagine going on forever, in the limit we actually reach 1. Okay? And this idea of looking at an approximation and seeing what happens in the limit is a central core concept in calculus, and you'll see it many times in this course. Now there are lots of other numbers, interesting numbers on this real number line. If I look just below 1.5, there's a number called the square root of 2. Now the square root of 2 has a decimal expansion 1.41421 and so on. Now this differs from the other examples. No matter where you look in the decimal expansion of the square root of 2, you never get a repeated pattern of digits that goes on forever. Okay? The square root of 2 turns out not to be a fraction involving counting numbers. It's said to be irrational, and that's an idea that we explore in the next video on the theorem of Pythagoras. What is the square root of 2? Well, it's a number whose square is 2, literally. So if I take a square, okay, whose side lengths are this number, the square root of 2, when I multiply these two numbers together, I get an area which is exactly 2 square units. Now there's another number, very important number on this line, a little bit more than 3. This number is called pi. And its decimal expansion is 3.14159 and so on. And like the square root of 2, no matter where you look on the decimal expansion for pi, you will never get a sequence of digits that repeats forever. Right? Pi turns out also not to be a fraction. The verification of that, in fact, is quite sophisticated, and to see that you would need all the tools that we develop in calculus in this course. Pi is defined in terms of circles. If I take a circle and I create a diameter, and I look at the perimeter, call that P, pi is in fact defined to be the ratio of the perimeter to the diameter, the fraction formed by dividing P by D. Now this is not a fraction involving counting numbers or integers, it's a fraction involving real numbers. And it's an amazing fact that no matter what circle I choose, no matter how small or how large, this ratio, P divided by D, is the same. It's not obvious. It's a fact that most people take for granted. And the reason it's true, in fact, is because all circles can be approximated arbitrarily well using similar triangles. And it's a fact from geometry that ratios of corresponding sides of similar triangles are equal. And that fact, when you take the limit, using a limiting process, that produces this fact that pi is constant for all circles. Now, in real life, we can't use infinite decimal expansions of numbers. When we come to apply numbers, we have to use a finite number of decimal places. For example, on your calculator, you'll read a display with maybe 8 or 9 or 10 digits, depending on how powerful your calculator is. You certainly don't see an infinite decimal expansion of a real number. For example, a third as an abstract real number is 0.3 repeated. But if I decide to truncate, if I just read the first 3 decimal places, I get 0.333. So instead of equals, I've actually got approximately equal. A third is approximately equal to 0.333 to 3 decimal places. Okay. Now 2/3, which is 0.6 repeated, if I truncate at the 3rd decimal place, instead of 0.666, I round up to 0.667. To 3 decimal places, this is closer to 2/3 than 0.666. So in that other example we had, 6/7, remember that's 0.857,142 repeated. If I truncate that at the 3rd decimal place, I get 0.857. If I decided to truncate at the 1st decimal place, I'd actually round this up to 0.9. Okay, so there are 2 different approximations to 6/7. One is more accurate than the other, to 3 decimal places, but the most accurate approximation to 1 decimal place of 6/7 is 0.9. Okay. Now the real number line is equipped with an arithmetic. You can do addition, subtraction, multiplication and division. And there are various rules for handling approximations when you apply these arithmetic operations. Okay, the first rule, when adding or subtracting, quote your answer to the least number of decimal places that is used. The second rule, when multiplying or dividing, quote your answer to the least number of significant figures that are used. I'll explain what significant figures are in a moment, but let's just illustrate the first rule. Okay, suppose I have a length, which I've measured correct to 1 decimal place, say 9.4 centimetres. Then I want to add to it another length, which I've measured carefully, this time to 2 decimal places, which is 2.13 centimetres. Okay, when I combine the 2 lengths, I have to add these 2 numbers together. So the combined length is 9.4 plus 2.13, okay, and that's 11.53. Okay. Now the 3 in the 2nd decimal place can't be relied upon because the coarsest measurement is the 9.4. Right? Because the coarsest measurement is to 1 decimal place, I'm not entitled to quote the answer to 2 decimal places, so I approximate this to the nearest number to 1 decimal place, which is 11.5. Okay, similarly with subtraction, suppose I take this length, 9.4 centimetres, and I remove a segment which I've carefully measured to be 2.13 centimetres. Okay, so what's left is the difference, 9.4 minus 2.13, which is 7.27. Okay, once again, this 7 in the second decimal place can't be relied upon because of the coarseness of the measurement of the 9.4, which is correct only to 1 decimal place. So again, you round your answer to the nearest number to 1 decimal place, which is 7.3. Okay, let's do an example with multiplication. Suppose I take a rectangle which is 9.4 centimetres wide and 2.13 centimetres high. Right, so the area is obtained by multiplying the numbers together. 9.4 times 2.13. Okay, if you type that into your calculator, it's a little bit hard to do in your head, you should get 20.022. But not all these digits are significant. You don't expect to be able to quote this answer to this degree of accuracy. The rule for multiplication is that you quote your answer to the least number of significant figures that appear in each of the numbers that are used in the arithmetic. The number of significant figures is the number of digits, regardless of the decimal point. So the 9.4 uses 2 significant figures, the 2.13 uses 3. So we quote our final answer to 2 significant figures, which gives you an approximation of 20 square centimetres. Now if I just say 20 square centimetres without reference to the original problem, it's ambiguous. You don't know whether I'm saying this rectangle is 20 centimetres correct to the nearest unit or possibly to the nearest 10 units, right? Is it 20 to the nearest unit or 20 to the nearest 10 square centimetres? Okay. Now it may look a little bit pedantic, but to be more precise, you could write this as 2.0 times 10 square centimetres. And the fact that you've written 2.0 means that this 0 in the expression is significant. Okay, so this is correct to 2 significant figures. Now if I wrote 2 times 10 square centimetres, because I've deliberately only written one digit, the 2, you know that the answer is correct to the nearest 10 square centimetres. So I'll give a more elaborate example. If you look, say, at the radius of the Earth, I believe that's 6,370,000 metres. Okay. Now if I just quote that number to you, you don't know whether any of those zeros are significant in the accuracy of the radius of the Earth. And in fact, the Earth is not a perfect sphere. Right? The radius changes as you move around the Earth. When I quote this radius, in fact, only 3 digits are significant. It's not obvious in the way the number's represented, so to emphasise that only 3 digits are significant, we express this in what's called scientific notation. I only list 3 digits, and we put the decimal point between the first 2 digits. And to recover the original measurement, we multiply by an appropriate power of 10. So the radius of the Earth in scientific notation is 6.37 times 10 to the 6 metres. And then the person receiving this information knows that you're only quoting the first 3 digits as accurate in this estimation of the radius of the Earth. Now, we've covered a lot of ground in just a few minutes, and there are many important ideas. Everything we've touched on is carefully explained and expanded in the notes accompanying this video. If any of these materials require clarification, please make a posting on the online discussion forum. We welcome your input and feedback.